I'm Dohyun Kim, and I'm at Brown, and this talk is with the Brandon Kiss at Brown University and Thomas Sorik at Simula and Boyan Lavrov in Lawrence Livermore. And today I'm gonna talk about the SiMPL method for topology optimization. So the sample is coming from sigmoidal mirror descent with projected latent variable. So to begin, we firstly explain about the topology optimization. So the hello world problem for the topology optimization is the compliance minimization. So for a given external force, we try to find the optimal material distribution in the design domain. Right. So we have a density here. Low equals to 0 implies that there's no material. 1 means that we place the material there. And we have additional constraint on the density field. So we have a volume constraint. So it does not exceed a certain percentage of the given domain. And we also have PD constraint here. So we need to solve elasticity equation in the every iteration of the topology optimization. So for the density-based topology optimization, so we replace this low to R of low is this is called the solid isotropic material penalization. So this promotes us to have like a binary design when we relax this density to be varying between 0 and 1. So instead of have 0 or 1, we allow density to be varying between 0 and 1. And also we have this filter equation here. So we have low tilde, which is called filter density. So this introducing this filter density allow us to have a mesh independent design at the at binary resolution. The goal of this talk is to introduce a new method called the SiMPL method for topology optimization. And this one has really favorable properties. So it is pointwise feasible solution at each iteration. That means that we have solution that preserves the bound pointwise, even when we use higher polynomials. And we want this method to be easy to implement. So you can see on the right, so we have like basically gradient descent like updating here. And we don't want to solve like a larger system to make this work. And so it does not require any additional memory or large system solve. And we want to obtain a very fast convergence here. Right? So this SiMPL A and SiMPL B is our method. So it converges like within 40 iterations, while other methods failed to converge or took much longer time to converge. So this preliminary result of this work is already on MFEM MFEM example. So example 37, if you're interested in, then please take a look. Yeah, so the main idea of this method is very similar to the projected gradient descent method. So for the unconstrained gradient descent method, so we update our design by just minus alpha k, the step size and the gradient at the current iteration. Then we update our design. So this is actually equivalent to solving this local minimization problem. So we replace the objective function by first order approximation, and we add some L2 regularization term here. So after removing the constant terms, then we obtain this final subproblem. For constraint minimization problem, so we have a bound constraint in the density and also the volume constraint. Then we need to this method is so-called projected gradient descent method. So instead of finding the density in the vector space, we find this one inside of the constraint set. Then the update rule becomes like this. So instead of having just gradient descent update, we also have projection operator here. This projection operator is just the L2 projection. So we have clipping, and then because of the volume constraint, we have volume correction term appears in here. So the mirror descent method is a generalized version of the gradient descent method. So instead of having this L2 regularization term, so we replace this by some exotic function d bar phi, which is called the Bregman divergence. So this Bregman divergence, we have this bar phi here. This one is a convex function, and the formula looks like this. Right? So for a convex function, we always so for given 2 points that we want to measure the distance, we firstly put a first order approximation here. This one always smaller than the entropy function that we used to here verify, and the distance between the entropy function at the other point and the first order approximation will become our Bregman divergence. So if phi is strictly convex, then so is the Bregman divergence at the first argument. But this one is not symmetric, and it does not satisfy the triangle inequality. So this is not a distance no. So why do we care about this one? So before we go in, so this is actual update formula if we solve this problem. So we have something similar to the gradient descent, but we have gradient of bar phi, gradient of bar phi inverse, and the projection is also the Bregman projection here. So it looks like we're making the problem really complicated. But the good thing about this Bregman divergence is that we can choose verify whatever convex function that we want to use. So then we can also think about a verify entropy function verify that encode our upper and lower bound of the density. So as you can see, this one is called the Fermi-Dirac entropy. So because of this logarithmic term, so we have the domain of this entropy has bound lower bound 0, and because of the second logarithmic term, we have upper bound 1. So this is encoded into our entropy function. So if we take a look at its gradient and the gradient inverse, then this gradient inverse is actually sigmoid function. So this sigmoid function defines a mapping between our constraint set to a non-constrained vector space here. So the bound constraint is removed in the latent space, colored green, and we can identify a point in the primer space or the left space by using sigmoid inverse and the sigmoid function. So now let's go back to our projected descent mirror descent method. So now this gradient of bar phi maps our density function into this latent space, right? And if we just replace this gradient inverse by sigmoid and this one by sigmoid inverse, then we obtain this update formula. So this part is now a gradient descent step in the latent space. And then this transformation is actually linear in the latent space, but in the primer density space, this is nonlinear transformation. Then because of the volume constraint, we also have to do the projection here. So this volume projection is actually just, we can just solve a Scala equation to satisfy the volume constraint like this. So we do the similar to the gradient descent method, but we are doing it in the latent space, and then we realize the density by using the sigmoid function. So we have talked about the latent space, and we call this psi as our latent variable. And if we take a look at this update rule for the density, then we have sigma inverse here, sigmoid inverse. This one actually has this logarithmic transformation. Because we want to have some binary design, so rho should go to 0 or it should go to 1. Right? then this taking logarithmic of this quantity is really numerically unstable. So to avoid this one, we take sigmoid inverse on the both sides. And then this one is just our latent variable at case iteration. Right. So now we have really nice looking update formula here. And then instead of finding approximation of our density, we find approximation of the latent variable. Then we can realize our density as sigmoid of the latent variable. The major benefit is that we now update rule is, instead of we have nonlinear update rule, in the latent space we have linear update rule plus one scalar equation here, nonlinear equation. And we no longer have to take a logarithmic transformation of near 0 or 1. And the bound constraint is satisfied pointwisely because of this sigmoid function. So if we think about high order polynomial that approximate discrete solution, then the standard population usually suffer from this highly oscillatory behavior. But if we have large oscillation in the latent space, then this large oscillation will gonna smear out in the primer space because the sigmoid of two large quantities are almost the same. So this kind of large oscillation at like far away from 0 will gonna not visible in the primer space. So it is really well suited for higher order approximation. So in here we have this alpha k. Right? To obtain fast convergent algorithm, we need to choose alpha k very carefully. So in the preliminary work that introduced this method is here. So this method was called the proximate Galerkin method, and it was one example of the proximate Galerkin method. And in that paper, we have experiment like this. So we take alpha k to be linearly growing with some fixed constant 10 or 25 or 50. You can see here, this blue line is alpha k equals to 10k. And you can see that if we take a larger step size, then it actually converges faster. But if we go too aggressive, like in the 50Ks, then we observe really oscillatory behavior, and the final design is completely off from the other two designs. So it is important to choose to large step size to get faster convergence, but we also have to be very careful because we don't want to have this kind of design. So the convergence analysis of the mirror descent method sometimes involves this relative smoothness. So this one looks a little bit unfamiliar, but if we replace this gradient of phi by the L2 norm, then this condition is the same as the ellipsis continuity of the gradient. But because we are working with Bregman divergence, so this is the some different version in the Bregman divergence. So in the gradient descent method, we usually want to have our step size to be smaller than this ellipsis constant inverse. So that is what we can do here. So instead of having the analytical value of L, because it is not known a priori, so we can approximate this L by putting two previous iterations into this equation. So we have approximated value of L, and we take the step size to be 1 over L here. And we further utilize the backtracking line search algorithm. So we have two types of backtracking line search. One is Armijo rule, and the other is Bregman rule. So on the left, we have the Armijo rule here. So it basically measures the sufficient decreasing condition with the user-defined parameter C1 here. And on the right, we have Bregman rule. So this one also ensures the monotone decreasing objective function, but it involves the analysis a little bit more. But this one is called Bregman rule, and we call this method if we use backtracking line search with the Bregman rule, then we call it a simple B method. So all of those methods has been implemented in MFEM, and we also have comparison with MMA and OCM, which are the one of the standard methods that we want to solve when we want to solve topology optimization. And because we are doing, we derive optimization algorithm in infinite dimensional space, and then we discretize, we expect our method is mesh independent. That means that to obtain the similar quality solution, the number of iteration does not grow as we refine the mesh. And also we have some examples other than compliance minimization. And yeah. But before we move on, I would like to thank Lincoln here, and he has pull request in the MFEM that implement this MMA, so that I don't have to write down my own version of MMA in MFEM. So the first example is MBB problem, beam problem. So we use the H is 1/256. So here on the left, we have a mirror boundary condition. So we do not allow the displacement go in this direction or this direction. And on the right, we have roller support. And we push in the center line here. So it tries to resist this, this input force. So if we take a look at the convergence behavior, then the simple A, simple B, and the OCs showed similar behavior, but MMA has a little bit slower convergence in the compliance. And if we take a look at the successive difference, and we also observe similar tendency here. And for the KKT condition, we have our method converge much faster than the other two. And here we have the final objective function value here. So OC is a little bit higher than the other three, and we have a similar objective function at the final design. And so we have used the backtracking line search algorithm. So in practice, people don't try to use backtracking algorithm because it costs too much. Right? So because when we want to evaluate our function, then we have to solve two PDs at each evaluation. So if the backtracking line search fails a lot, then we have more computational cost. But in here, the number of the difference between the number of iteration and the number of evaluation is the number of failure of our backtracking line search. You can see that with the guided initial guess that we have chosen in previous gives a very good step size, so that we only have like one or two failure during our optimization process. The simple B is a little bit more conservative, so it has more number of re-evaluation, but the overall is still have like a much smaller computation cost compared to the other two methods. So this is the result, and yeah, now we have simple A and simple B both converged, but OC, it looks like we have black and white design, but the MMA we still have a very grayish design. No, and we can accelerate this MMA by manipulating the scale of the gradient, but we haven't done do this yet. But at the final design, you can see that this MMA simple A, simple B showed almost the same design, but the OC has one more connection here. And yeah, so this result are all with the constant piecewise constant density, but we mentioned that it also works for higher order polynomials. So if we use a fourth order polynomial with a much smaller mesh size, then we still obtain qualitatively similar design at the end. So, and we also observe the number of iterations that by defining mesh sizes. So this is mesh size with 2 to the minus 6, minus 7, and minus 8. And we have similar design at the end. And also the convergence behavior is almost exactly the same between different method and a bit different backtracking line search and also different mesh sizes. And so we have like really good mesh independent behavior in the and we also have a 3D example here. So in this case, we fix the left boundary here and we apply a force on the right bottom. And in the 3D, we obtain this result with only 44 iterations. It converges much faster than the usual first order algorithm that topology optimization people would. And we also consider the self-weight compliance minimization. So in the previous, we only have spoiler, and in the previous, we only have external force, but in addition to external force, we also have a gravity on the, so it has to support its own weight. And yeah, if we solve this problem, then in the middle of the optimization process, we have a little bit of support appear in the middle, but as soon as they form some support connection between the platform and our main support, this auxiliary support will gonna disappear. Yes. And then at the end, we have a bridge-like design. This one is obtained after like 81 iterations. And the last example is the compliant mechanism. So in here we have we fix both ends and we push from the bottom, and we want to have a design that maximizes the output displacement on the top, like here. And to solve this problem, we have three different initial condition, initial guess. So the first one is just we put constant density, and the other we have a little bit of information. So we know that it should be connected to this fixed support, and also it should have some mass in the input and the output port here. So we connect those points with some interior point here. In this case, we placed it in the middle, and in this case, we placed on the boundary. So here, regardless of the choice of the initial condition, we obtain similar design, but because it has a lot of local minima, so we obtain slightly different design depending on the initial condition. So those are obtained with like 163, 126, and 89 iteration. So the changing the initial guess affects the number of iterations a lot. But our methods can converge even if there is no initial guess at all. So we have introduced the SiMPL method for topology optimization. The solution at each iteration is pointwise feasible, so because of the sigmoid function, and the update in the latent space is very easy to implement, and the computational cost at each iteration is equivalent to the gradient descent method. So we only have to compute the function and the gradient, and the number of failure for backtracking line search is not too much. And this allows us to have like fast and stable convergence, and it also performs a standard method in the topology optimization in all benchmark problems that we have tested. So we have mentioned about the high order method. So I highlighted one fact about the high order method is that in the process, we have to solve the filter equation, and that filter density also should satisfy the bound constraint. So in the previous example, I just clicked the density filter density, but we can also utilize the proximal Gallatin paper that we mentioned before to obtain also bound preserving filter density. So then we can actually use higher order method without any clipping. And we also want to extend this idea to multi-material topology optimization. So by we can employ different entropy to achieve this goal. And for a more general constraint, we are also planning to extend this idea to other types of constraint too. And yeah, that's all for talk, and thank you.